I am Dr. Sharmishta Lahiri from Sri Aurobindo College. I am teaching physics, associate professor in physics in Sri Aurobindo College. Today's lecture I will be talking about the lattice vibrations of a diatomic chain of atoms. In my last lecture I talked about the monoatomic chain of atoms, lattice vibrations in a monoatomic chain of atoms. The books I will be consulting in this for this lecture will be Introduction to Solid State Physics by Charles Kittle, Solid State Physics by M.A. Wahab, Solid State Physics by R.L. Singhal, Solid State Physics by Ashraf and Marmee. In this diagram shows a linear diatomic lattice. Let us consider a diatomic lattice having atoms of two different masses, small m and capital M. Small m is the lighter mass and capital M is the heavier mass. As we had talked about in my last lecture, we assume that these atoms, they are connected by ideal Hooke's law spring. In a lattice, they are connected by ideal Hooke's law spring. That means any distortion that is produced in one will be transmitted to all the other atoms via the nearest neighbor, and because these springs are assumed to be ideal Hooke's law spring, this means that the distorting force will be proportional to the distortion. So, let us consider that a small lighter mass small m, which is at position 2n. Let that be the center. On the right of it, and these masses, the heavy and the lighter masses, they are placed alternate to each other. The one next to the lighter mass, which is placed at 2n, is the 2n plus 1th mass, which is the heavier mass. The next will be 2n plus 2th 1, which will be again a smaller mass small m. The two masses are small m and capital M, and on the left, the one on the left will be 2n minus 1th mass, which is the heavier mass capital M. 2n minus 2th will be the lighter mass small m. Now, let us assume that there is a vibration that is produced in the lattice, and because of that the 2nth mass is distorted from the equilibrium position by an amount u2n. The motion of the 2n plus 1th mass will be given by u2n plus 1, to the 2n minus 1th mass will be u2n minus 1, and so on and so forth. Okay. So, I am considering two different masses, and let A be the separation between the two nearest neighbors. That means two of the lighter masses small m, lighter masses will be at a separation of 2A. Two of the nearest neighbor, that is one heavy mass and a lighter mass, will be at a separation of A, and two of the masses of same masses will be at a separation of 2A. Let beta be the spring constant of the masses. Then to analyze the equation of motion as we did it last time, the force on the 2nth mass, let it will be F2n, that will be equal to m d square u2n by dt square, which should be equal to beta u2n plus 1 minus u2n plus u2n minus 1. And the force on the 2n plus 1th mass will be capital M d square u2n plus 1 by dt square. Now, the two masses, because we are considering a diatomic lattice consisting of two different masses small m and capital M, therefore, we have to write two different equations of motion. This will be equal to beta u2n plus 2 minus u2n plus 1 minus 2 u2n plus 1 plus u2n. Then in this case again we make the assumption that each of the atom it interacts only with its nearest neighbor, and the force constant is identical between the nearest neighbors. All other atoms interact with all other atoms via the nearest neighbor. Now, for equation 1, the running wave solutions will be of the form U2n equal to A e to the power of I omega t minus 2n Ka, and U2n plus 1 will be B e to the power of I omega t minus 2n plus 1 Ka. In this case, because there are K is the wave vector of a particular mode. Now, because there are two different masses, so the amplitude A and B will be different in this case. The frequency of the two types of atom, they are taken to be the same, because both the atom types, they take part in a single wave motion K. The amplitudes are different because of the difference in masses. Now, we can write similar equations for U2n plus 2 and U2n minus 1. So, we substitute these equation number 2 and other equations which we write for U2n plus 2, similar equations for U2n plus 2 and 2n minus 1, substitute them back in equation number 1 and solve for it. We will get two sets of equation. Minus of small m omega square A should be equal to beta B e to the power of minus I Ka plus e to the power of I Ka minus 2 beta A, and the second one will be minus of capital M omega square capital B, M omega square B will be equal to beta A e to the power of minus I Ka plus e to the power of I Ka minus 2 beta B. Now, cos theta, cos of Ka, we can write it as e to the power of I Ka plus e to the power of minus I Ka by 2. So, twice of cos Ka will be equal to e to the power of minus I Ka plus e to the power of I Ka. This we substitute back in equation number 3, then we separate out the variables. Then equation number 3 will take the form 2 beta minus omega square m into A minus of 2 beta cos of Ka B should be equal to 0, and minus of the other one will be minus of 2 beta cos Ka into A plus 2 beta minus omega square capital M into B should be equal to 0. These two equations I label as my equation number 4. Now, solution, these set of equations will have a non-vanishing solution only when the determinant of the coefficients of A and B vanishes. So, if I write in the determinant form 2 beta minus omega square m small m and 2 beta Ka minus of 2 beta cos Ka 2 beta minus omega square capital M, the determinant of it should be equal to 0. Solve for the determinant, that takes the form of 2 beta capital M omega square multiplied by 2 beta small m omega square minus of 4 beta square cos square Ka should be equal to 0, or this after rearranging takes the form omega to the power 4 minus of 2 beta m plus m upon mm omega square plus 4 beta square sin square Ka upon mm should be equal to 0. This is a quadratic equation in omega square. Now, to solve for and this will have a solution of the form, because it is a quadratic equation, the solution will be omega square should be equal to minus of b plus minus under root of b square minus 4ac upon 2a, that is the standard solution. So, omega square will take the solution, omega square will be of the form beta omega square should be equal to beta 1 by small m plus 1 by capital M plus minus under root of 1 by small m plus 1 by capital M whole square minus of 4 sin square Ka upon m into mm. This equation I label as my equation number 5, and this is the dispersion relation for a linear diatomic lattice. Omega values will be the square root of the term on the right hand side. Now, in this case what we find is that omega will be the square root. So, for each value of omega, because there is a plus minus sign in before the second term, so for each values of omega, there are two possible values for a single wave vector k, and in this case we are only considering when I am taking the square root of this equation of the right hand side of the terms of equation 5, I am considering only the positive part, because a frequency can never be a negative quantity. So, we have to consider only the positive part when I take the square root of this entire quantity on the in the right hand side. Then what we find is, yet for all the values, even when I take the positive quantity, because there is a plus minus sign in front of the second term, so for each value of k, there will be two possible values of omega. Now, let me label them as omega plus and omega minus, corresponding to the positive or the negative sign that I am taking for the second term of equation 5. Now, let us consider the quantity omega plus. Omega in the limit k tending to 0, we can neglect the sign term. In the limit k tending to 0, the second term in this equation in the under root part can be neglected. So, that takes the form, the sign term is can be neglected, k tending to 0, sin square k will tend to 0. So, I can neglect that term, and omega plus will take the form under root of 2 beta 1 by small m plus 1 by capital M. Okay. Only the positive root of the positive root will be taken, because frequency can never be negative. Now, for the limit k tending to pi by 2a, then the sign term will be relevant, and that will be equal to minus 4 by mm by expanding the sin theta and then taking the first term. Then what we find first order term, then omega plus will take the form under root of 2 beta by small m. That means for k tending to 0, omega plus takes the form under root of 2 beta 1 by small m plus 1 by capital M, and for k tending to pi by 2a, omega plus becomes equal to under root of 2 beta by small m. Now, consider omega minus. Again, for k tending to 0, the sign term that becomes equal to, that cannot be neglected. So, by expanding, making a Taylor series expansion and then taking only the first order term, we get that to be equal to 4 k square a square by mm. So, omega square will be of the form ultimately. So, we substitute that, do the necessary calculations, and omega square will become equal to 2 beta by m plus m k square a square, or omega minus will be equal to k into under root of 2 beta upon m plus m. Again, for the limit of k tending to pi by 2a, then that we find that omega minus will be of the same form as my equation number 7, but instead of 2 beta by small m, it will be under root of 2 beta by capital M. That means, in the limit of k tending to pi by 2a, at k pi by 2a, omega minus will be under root of 2 beta by capital M, and when k tends to 0, omega minus becomes equal to k tending to 0, that becomes equal to k a into under root of 2 beta upon m plus m. That means, at k equal to 0, omega minus will be equal to 0. So, this is the dispersion relation. Now, if I plot it, what we find is this will be the dispersion relation. In this dispersion relation, the omega minus is called the acoustical branch, now instead of a single variation, omega for every value of k will be split up into two branches. The lower branch is called the acoustical branch, omega minus, that is the plot of omega minus, and the upper one is called the optical branch, which is a plot of the omega plus. At k equal to 0, omega minus is 0, and at k equal to 0, omega plus will be under root of 2 beta 1 by small m plus 1 by capital M. The interesting fact is at pi by 2a, omega minus will be equal to under root of 2 beta by capital M, and omega plus will be equal to under root of 2 beta by small m. That means the allowed observations is, as I said, the allowed frequency range of propagation is split up into two branches. The upper branch, which is omega plus, plot of omega plus, is called the optical branch, and the lower branch, which is a plot of omega minus, is called the acoustical branch. That means there are two modes for every value of k, two possible values of omega for every value of k. Also, there is a band of frequencies between the two branches for which wave-like solutions do not exist. That is marked by that will be the called the forbidden frequency branch. In between the two branches, there is a region of omega which do not have any allowed solutions, and though that region is called the forbidden branch. It is not possible to excite the vibrations of frequency which is lying within this branch, and this branch, as I said, is called the forbidden branch. The width of the branch will depend on the ratio of capital M by small m. Larger this ratio, capital M by small m, wider will be the frequency band. As you can see from this figure, optical branch at pi by 2a, it is under root of 2 beta by small m. The acoustical branch omega minus is under root of 2 beta by capital M. So, the width of this band, this forbidden band, will depend on the ratio capital M by small m. Now, the two masses, they will be, if the two masses are equal, that is small m is equal to capital M, then the two branches will join at k equal to plus minus pi by 2a. And the first Brillouin zone in this case goes from minus of pi by 2a to plus pi by 2a. Therefore, the smallest possible wavelength, now k is 2 pi by lambda. So, the smallest maximum value of k possible is minus pi by 2a to plus pi by 2a. So, a lambda, smallest possible value of lambda will be equal to 4a, and that corresponds to pi by 2a at the zone boundary. What is the physical difference between the vibrations which is represented by these two branches? Let us calculate the A by, to know this, let us calculate the A by B ratio for the two branches. For the optical branch, that is the omega plus, at as k tends to 0, cos of k will tend to 1. So, equation 4 will take the form minus of omega square small m into A should be equal to 2 beta B minus 2 beta A, or omega square by 2 beta will be equal to minus of B minus A upon M into A. Now, the second equation, in equation number 4, there were two parts, 4a and 4b. The second equation will take the form as cos k A tends to 1. The second equation will take the form of minus of omega square capital M into B should be equal to 2 beta A minus 2 beta B, or again if I rearrange that, that will take the form of omega square by 2 beta should be equal to minus of A minus B upon capital M into B. By equating the RHS side of omega square 2 beta from these two equations, we get A minus B upon capital M into B should be equal to B minus A upon small m into A, or A by B should be equal to minus of small m by minus of capital M by small m. A by B ratio should be equal to minus of capital M by small m. This indicates that the two masses, they are moving in the opposite direction. The negative sign indicates that the two masses, they are moving in the opposite direction. Also, A and B are the amplitudes of the amplitude of vibration of the lighter mass and the heavier mass. Then these two amplitudes, they are inversely proportional to their masses. What we find is the two masses, they are moving in the opposite direction. Also, their amplitudes, they are inversely proportional to the masses. That means for the optical branch, as k tends to 0, the masses, they are moving in the opposite direction and their amplitudes, they are inversely proportional to the masses. So, this means that the CG of the system will remain stationary. This is indicated by the first figure. The heavier amplitude of the heavier mass will be smaller, amplitude of the lighter mass will be larger, but the entire system, the CG of the entire system will remain stationary. That is indicated by the first figure. If I go back, then what happens for the acoustical branch? Now, let us see. Acoustical branch is omega minus. As k tends to 0, cos of k, we cannot take it to be equal to 0, otherwise entire system becomes equal to 0, everything. So, this can be expanded as 1 minus k square a square by 2. So, again from equation number 4, I can write the two equations as minus omega square small m into A should be equal to 2 beta B into 1 minus k square A square by 2 minus 2 beta A, and the second one will be minus of omega square B omega square m B equal to 2 beta A 1 minus k square. Now, if I add these and then calculate, what we find is that the A by B ratio in this case will be equal to 1. This means that the two masses are moving in the same direction with the same amplitude, and their amplitudes are independent of their masses. This is indicated by the second figure. Then that is the case of then optical mode, the neighboring masses, they are moving in the opposite direction. Acoustical, they are moving in the same direction. The acoustical branch can be excited by the sound waves, the optical branch can be excited by light waves. Ionic crystal, when two branches, two atoms, for example, if I think of sodium chloride, there is the sodium Na plus ion and the Cl minus ion. They are moving in the, that means the two sublattices, they can be excited by irradiating with a beam of light, that is the optical branch. And other one, this must be, this type of excitation will depend on two atoms per primitive cell. Now, if I go to the two, if the two masses are equal, then what we find is it behaves as a monoatomic lattice, but there will be and entire system for the monoatomic lattice, entire omega varies from 0 to 4 beta by m omega square, or omega varies from 0 to 4 beta by m. In the diatomic case, omega square will vary from 0 to 2 beta by m and 2 beta by m to 4 beta by m. One will be the acoustical branch, next will be the optical branch. As the heavier mass increases, then what we find is the acoustical branch will move down, and ultimately when m tends to infinity, it will be lying along the k axis, and the optical branch will again have a constant value all throughout, having under root of 2 beta by small m. As the lighter mass increases, then the optical branch will shift upwards when small m tends to 0, optical branch it disappears completely, and the acoustical branch is the only one that will remain. That means in this case the two sublattices, lighter mass monatomic case, a plot of B by A versus K will be given for the acoustical branch at K tending to at K equal to pi by 2a and minus pi by 2a, it tends to infinity. For the optical branch it will become equal to 0, and it will be for the acoustical branch B by A ratio will be 1 at K equal to 0. Now this means that B by A is infinite for the acoustical branch, and it will be lighter branch optical and the K pi by 2a acoustical branch, and the all the atoms of the acoustical branch are at rest, that is capital A equal to 0. Optical branch, in the optical branch all the atoms of heavier mass are at rest, that means capital B equal to 0. That means in this case only one of the sublattices is vibrating. So if there are capital N number of atoms per primitive cell, then it would split into N number of bands. If I consider the normal modes of vibration and consider the periodic boundary condition, that means the vibration of the first and the last atom is the same, then UN displacement of x and x plus L will be same. If I write the equation and calculate, then K will be equal to plus minus pi by L plus minus n pi by L and so on and so forth. That means K cannot have any arbitrary value, rather K will have only certain definite values. The crystal cannot propagate all frequencies, only certain allowed frequencies are propagated down a crystal, and that is this is the forbidden branch. Phonons lattice vibration, this means that the elastic vibration of a lattice is quantized, and this quanta of lattice vibration is called phonon, and the phonon momentum will be given by hk by 2 pi. Okay, that's all for today. Thanks.